we talk about the element matrix equation. So I got a question of the class is like in this two spring element system, we can always write something like this, like K1, negative K1, negative K1, K1. Yes, it's correct. So for the spring element, and we will talk about the bar element soon. For this 1D element, we can always have this K matrix. The only thing different is K for different element may be different. So the K1 and the K2 may be different thing, but we can always have K matrix in the form like this. Why is that? We had derivation from the element equilibrium equation. And we know that the force, nodal force and node J is K Uj minus Ui, and node I is always opposite, same magnitude, so it becomes Ui minus Uj. So when we put these two equations into matrix form, we can always have K1, negative 1, negative 1. So this K matrix stay the same for all our spring element matrix equation. So this is for the element equilibrium equation, and we talk about that for the K for element equilibrium equation is always K matrix is always singular determinant 0. And if we have system combined with multiple spring elements, and we combine them into a big matrix, of course, if this one determines 0, this one determines 0, this 3x3 matrix, of course, determinant 0 is just singular. And the way to solve this, to remove this singularity of the matrix is that we need to apply boundary condition. And the way we apply boundary condition is that for the row, that because F1 here in this example, F1 is a reaction force, and in FEA, reaction force is always unknown force. I know for some of you can see that, okay, this is F2, this is F2, that's F3, and I know that reaction force should be F2 plus F3 in the negative. No, we don't do that. This is a simple situation, of course. This is beginning of semester. You can just look at it, the reaction force based on what you learned from statics. But remember that in our FEA, when we get more complicated, you don't normally can just see the problem, you know what is reaction force. So we just always assume that reaction force are unknown force. So back to this one, since we have matrix given information times something unknown we need to solve equal to the force vector, we do want everything, and here are given information. But if this one becomes reaction force, this one is unknown. So this one times this one equal to F1 is kind of useless information. That's how we apply boundary condition. We delete the first row, right? And another thing is that, again, since this is a boundary condition, we know that U1 should always be 0 because it's fixed here. It cannot move. So again, back to the matrix vector operation, anything multiplied by 0 equal to 0. So this column doesn't matter anyway. I can have any random values here. It all times 0. So that's why we can delete the first column. And then after apply boundary condition, it becomes 2 by 2, 2 unknown degree of freedom, 2 known forces. And we can calculate inverses. This one becomes now non-singular, invertible. The determinant is non-zero, and we can have inverse of this matrix times this one equal to the unknown degree of freedom. So this is how we apply the boundary condition. So after we apply boundary condition, becomes the global matrix equation. And yeah, so this is the theory part. Any question? Oh, I forgot. Attendance. Yeah. Do you have paper? Yeah. So same on this side. Do you have paper? Yeah. Thank you. So still the printing name, UFID signature. Thank you. So this is the theory part. Now let's check a example problem. We have a spring system with 5 elements. So there's a small element, spring element between these two nodes. One element here. And one here. So for the node, let's put this the left side as node 1. This is node 2, node 3, node 4. So basically, you see these two blocks in the middle. This you can consider this node 2 and node 3. They are rigid body. So basically, the element connected to this node have the same. This node has the same displacement. The rigid body itself cannot deform. So 2 and 3, there are two nodes. And for the element, let's put as let's use element 1, 2, 3, 4, 5. We have 4 nodes, 5 elements. And force applied on node 2 is in the positive x direction, has 68 Newton. And force applied to node 3, 136. To simplify our calculation, I put it as K for element 1 equal to 1, element 2 equal to 2. And the unit, of course, is force per length, so Newton per millimeter for the K. Stiffness for the 5 spring elements. The question is that, of course, I know degree of freedom, U2, U3. We need to calculate displacement at node 2, displacement at node 3, reaction force at node 1, reaction force at node 4, and element force of the second spring element. But of course, I just use one as example here. You can use the same method to calculate element force in 1, 3, 5, 4, right? Same thing. If you know how to calculate 1, you know how to calculate all 5. How should we? I can share the note to you later. Yeah, it's okay. How should we start? How to solve, let's start from these two unknown degree of freedom. Boundary condition. First step, before we apply boundary condition, we need to have the matrix first, right? Yeah, how to what is the after assembly, what is the dimension of the matrix? 3 by 3. It's 3 by 3 before we apply boundary condition. Okay. Yeah. Okay, that's one opinion. So any other opinion? 2 by 2. Are you talking about before apply boundary condition or after apply boundary condition? Before apply boundary condition 2 by 2. After apply boundary condition, what is the dimension? So let's say this one is before we apply boundary condition is 3 by 3 matrix, and after we apply boundary condition 2 by 2 for our 2 spring elements. After, yeah.
So it would be 4 by 4 boundary conditions because it's 4 names, right?
Yes, thank you. And after apply boundary condition, it becomes
Boundary conditions.
what's the dimension of the matrix after we apply boundary condition? And no, before apply boundary condition, it should be 4 by 4 because we have 4 nodes.
Yeah.
How about after apply boundary condition? I heard someone said 3. Why 3? We have this side is reaction force. This side is also reaction force. You can consider this like clamped to 2 walls. These 2 walls cannot move.
But because the reaction from 1 and 4.
Yes, yes, yes. Thank you. So before we apply boundary condition, it should be 4 by 4 because we have no 1, 2, 3, 4. After we apply boundary condition, we do the rows and columns corresponding to node 1 and node 4. So we have 2 by 2 left. Make sense or not? Now, okay, your question. Yes. You can check this one. Now, for this system, you have 3 nodes, right? And 3 nodes means this is 3-degree freedom. But of course, this is simplest element we are learning now. If you go more complicated, let's say for the bin element, I talk about that each bin element has 2-degree freedom. It's deflection upward, displacement in the y direction, and also the rotation. So if you have one bin element, it should have 2 nodes, but it's not 2 by 2, it's 4 by 4 because each node have 2-degree freedom. Let's say node 1, node 2, we have V1, V2, theta 2. Right. So, well, right now we can say that yes, like the dimension of the K matrix depends on how many nodes we have. But later, when we learn more advanced elements, it's not really just depend on number of nodes. It also depends on how many degree freedom at each node. And if we talk about as a frame element, it has displacement in x direction, displacement in y direction, and rotation about the z direction. So now each node has 3-degree freedom. So if you have one frame element, it actually becomes 6 by 6 because the 2 nodes, each node have 3, right? So yeah, any other question? So now our job is how to find this 4 by 4 matrix. How to write this 4 by 4 matrix. So in your homework and in the exam, you can write this 4 by 4 matrix directly, or you can even have the, let's say, 2 by 2 matrix directly. Just write the after apply bound condition. That is fine. But since this is our first example problem, I'm trying not to skip any steps to make it as clear as possible. I will write the K matrix for each element and show you how to assemble them into a big 4 by 4 matrix. Since I already mentioned that this is our basic equation, right? This one, negative 1 doesn't change. The only thing change is the K. So now for our 5 elements, I can write 5K. Let's use different color. So for element 1, I use superscript 1 to represent the K matrix for the element 1, and it becomes 1, negative 1, negative 1, 1. And I also want to put the row and column index here. So when you do the assembly, it's easier. So this is it, representing U1, U2, U1, U2. Since element 1 is connected to node 1 and node 2. So it should be U1, U2, U1, U2. Similarly, for element 2, since for element 2 equal to 2 Newton per millimeter, let's write this one's 2, negative 2, negative 2, 2. And for the row and column index, I just write as for element 2 is connected to node 2 and node 4. So it should be U2, U4, U2, U4. Similarly, for element 3, we have 3, -3, -3, 3. And element 3 is connected to node 1 and node 3. So for the row and the column index becomes U1, U3, U1, U3. K4. 4, -4, -4, 4. And element 4 is connected to node 2 and node 3. So we have U2, U3, U2, U3. The last one. K for element 5. -5, -5, 5. And element 5 is connected to node 3 and node 4. So U3, U4, U3, U4. This is the K matrix for each element. It's always K, 1, -1, -1, 1. And we just need to be clear that what is the row index and column index for this 2x2 matrix, because this is very important, like how do you put it into the 4x4 matrix, where's the location of each component. This is basically determined by what are the two nodes is connected to. So for element 1, it's connected to node 1, 2. That's why 1, 2, 1, 2. Let's say for element 4, it's connected to node 2 and node 3. So that's why we have 2, 3, 2, 3. Any question? Okay, now let's see how to put it into a 4x4 matrix. So this is our first step. Second step, let's assemble them to a big matrix. The structure matrix equation. U1, U2, U3, U4. And right-hand side should be force at node 1, node 2, node 3, node 4, right? And of course, this force vector on the right-hand side of the assembly is the external applied force. And F1 is basically reaction force applied by this wall. Well, reaction force, in some sense, is also considered as external applied force because it's a force applied by the wall to our spring system. So it is reaction force is one type of external applied force. It's just unknown. And F2, F3, they are given. F4, the same reaction force. That's what is the force vector on the right-hand side. This is in our system, we have 4 nodes. Each node have 1 degree of freedom. So we have U1, U2, U3, U4. How to write this 4x4 matrix? How to write this? What are the components in this 4x4 matrix?
Five smaller matrices, and we'll see, like starting with U1, what the component of U1 is for 1, what the component is for 3, add that in.
Yes, yes, thank you. So basically, we are checking the row and the column index here, right? So let's say we have 1 and 2, 1, 2 here, and I can also put U1, U2, U3, U4. You just put it at the corresponding position. Let's make it clear. Let's say this is 4x4. We should have 16 components. Let's see how to put these 16 components in. So for the first element, we have 1, -1, -1, 1. Since it's U1, U2, U1, U2, so it should be this 2 by 2 position, right? So 1, -1, -1, 1. So this is for element 1. For element 2, and you can see that it's U2, U4, U2, U4, and U2, U4, U2, U4. So it should be this 4 position. Make sense or not? Okay. So now let's put the element 2. It becomes +2, -2, -2, and +2. Similarly, for element 3, it is U1, U3, U1, U3, U1, U3, U1, U3. So the 4 components should be here, here, and here. Make sense or not? Okay. So for element 3, we have +3, -3, -3, +3. And same thing for element 4, we have U2, U3. So -4, -4, +4. And for element 5, it has U3, U4. So U3, U4, U3, U4. So it should be these 4 components. -5, -5, +5. Any question here? Or this is like very clear for you guys? Do you guys know how to do the assembly? Like assemble the element K matrix into the big matrix equation. Okay, great. So and also you can notice that we don't have really components here and components here. This is basically there's no element really connected to node 1 and node 4. So let's say this is node 1, this is node 4. If I add one element here, then these 2 should be non-zero. But since now we don't have that element, it's just simply put 0 here and 0 here, and we're done for the 16 components. Now let's apply the boundary condition. Since we talked about that node 1 and node 4, they are the reaction force. So delete the rows that are corresponding to the reaction force. Let's use, I don't have color to use. Let's use purple. And also, I talked about that U1 equal to 0. Let's see. It's okay. U4 equal to 0. So any value in this U1, U4 column doesn't matter because it multiplies by 0. So we can delete this one and this one. And now it becomes 2 by 2 matrix after apply boundary condition. Right. So now let's write this matrix equation after apply boundary condition, and we can solve our unknown degree freedom U2, U3. So it simply becomes 7, -4, -4, 12. U2, U3. What should I put here for the force vector? What are 2 components? Yes, thank you. So of course I will skip the the actual calculation part, you calculate inverse of this one times this one, you get a U2, U3. So I will give you the U2, U3 directly. If you have a question, you can ask me.
Crossing out.
Yeah. So sorry, what's the question?
Well, what's the purpose of that reason?
Yeah, this is applied boundary condition because in our system, this is a boundary condition, right? This is clamped to the wall. This side is also clamped to the wall. So basically, node 1 and node 4, they are boundary condition. And as I said, boundary condition, the force at node 1 and node 4 is the reaction force. All the reaction force in our FEA are considered as unknown force. And yeah, if you see this system, you don't really know what is the F1 and F4. So these are the reaction force. And in this matrix vector operation, if these two are unknown, basically this one times this one equal to something unknown, this one times this one something unknown. These are useless information for our calculation temporarily. So that's why we did this row and this row, simply because these two are unknown. And then we did this one and this one is because we know that U1, U4, they're clamped to the wall. It cannot move. So U1 equal to 0 and U4 equal to 0. And again, based on our matrix vector operation, how you do the calculation, let's start from the second row, since the first row is deleted. This one, -1 times U1, this one times U2, this one times U3, this one times U4 equal to F2, right? But since now we know that U1 equal to 0, U4 equal to 0, it doesn't matter what is here, what is here. So we can just ignore these two columns. That's how we apply boundary condition. We always delete the rows and columns corresponding to the boundary condition. Yeah. They are not 0. Yeah. If just imagine, let's forget about FEA. If just simply from statics, if F1 and F4 equal to 0, and you have F2 and F3 applied, you just like fly away. Make sense or not? Or our FEA or mechanics material statics problem, they should be, our system should be in equilibrium. Yeah.
If it was only fixed at 1.
If there's only fixed at 1, good question. Then let's remove this one. And we have, let's put a rigid body here, but this rigid body can also move, right? That's what I mean. So basically, the 4x4 matrix should be still the same. The only thing different is that when we apply boundary condition, we can only delete this first row and the first column. Now, this one, if you don't apply force, let's put this one as a node, as a rigid body block. If you don't apply a force on this block, just like free there, it basically means F4 equal to 0. If you put it as a block and I apply a force here, then I put the force in the matrix in the vector, right? So the only thing different is that in the end, you have 3x3 matrix equation, and you solve the 3x3. And of course, in your homework, you can use MATLAB. And try to avoid any matrix vector operation higher than 2x2. Yeah. Any other question?
Will we be able to learn how to solve F1 or that is not solvable?
It's solvable or not solvable?
Not solvable.
I'm asking you. What do you think?
I mean,
you have 50% chance.
Yeah.
Yeah, how to solve it?
So I get back in.
Yes, correct. Yes. Since now using this 2x2 matrix equation, we can solve U2, U3, right? So basically 0, U2, U3, 0. And yeah, we're done. You're welcome. Thank you for the question. Any other question? Okay, let's put the U2, U3 here. U2 is 20 millimeter. So our force unit is given as Newton, and our K is given as Newton per millimeter. So displacement, it should be millimeter unit. U3 equal to 18. And of course, if you get positive value, means move to the positive x direction, equal negative value means move to the negative x direction. So now $20. This is 20, right? Yes, 20. So we are done with these two. How to calculate R1, R4? Someone already answered. Yeah, put it back in. So now, since we already have everything here, and R1 is same as F1, R4 is same as F4, because in this matrix equation, F1, 2, 3, 4, they are external applied force, and I already explained that boundary condition reaction force at boundary condition is considered one of the external applied force. It's a force applied by the wall to our spring system. So if you put U2, U3 into this vector, and this one times this one equal to F1, this one times this one equal to F4, and equal to R1 and R4, right? So R1 equal to F1 equal to, so again, this one times 0, this one times 0, these two terms doesn't matter. So we have -1 times U2, -3 times U3 equal to F1. Similarly, for R4 equal to F4, we have -2 and -5. And of course, when you see a negative sign, it means it's a force applied in the negative x direction. Makes sense, right? You can also, of course, double check with what you learned from statics. Two force applied to the left, two force applied to the right in the system. They are in equilibrium, right? Now, the last one, how to calculate the element force of the element 2. How to calculate element force of the second spring element. Of course, I'm just using the element 2 as example here. You can use this same method to calculate any the element force of any element. Yes, actually, you can just use this one, and you times U2, U4, and you have the nodal force, right? And nodal force, element force is always the same Fi, Fj, and element force are same magnitude, but element force is always the same sign as the Fj. If you remember our derivation here, so this is the element force. It's the same idea as the internal force we talked about in the mechanics materials. And these three always the same magnitude. And I already explained element force is always the same sign as whatever at node J, and opposite at node I. So since we already have the Ui, Uj, we can solve for the element force. U4 minus U2. -20. U4 is the second node of element 2. U2 is the first node of element 2. So this is element 2. U2, U4. So now this node 2 is a UI, node 4 is a UJ. And UJ equal to 0, of course, and U2 we already solved is equal to 20, so it becomes negative 20, and we get negative 40. And again, as I emphasized, the element force P is the same idea as the internal force we learned in mechanics material. So whenever you see a negative sign, it means compression. And it should make sense because if you check this structure, this is a wall. This is a rigid body. You apply the force in the positive x direction. It should be compression here. If you somehow solve a positive value, you should double check if you have some mistake in the calculation. Make sense or not? Any question for this example? Yeah. Yes. Yes. In real life situation, you know force, right? Yeah. So let's say a typical structural problem is that you know a structure. You know what is the load you need to carry, and you need to calculate if this structure is safe or not. So force is given. Force given means that direction and magnitude both are given, because force is a vector. And the structure, if you know what material you want to use, you know the Young's modulus. If you know the cross-section dimension, you have the cross-section area, or if it's bending, you know the moment inertia. So we normally consider that a typical structural problem is that you know the K, you know the F, you calculate Q. And using the node degree freedom, let's say U2, U3 here, let's say for bar element, you can calculate strain, you can calculate stress, right? So this is like the general idea of how to solve the structural problem. But of course, we can also do that. I know what kind of load we need to carry, and I need to design my structure, so I use it to, I have the displacement constraint. I don't want the displacement exceeding some certain value. I can consider the units given, and then I use to design like what material should I use, how strong the material I should use, and what is the cross-section area to use to design the K. So it's the same thing. Oh, this one? U4 equal to 0. U2 equal to 20. Right. U4 is clamped. This node cannot move. Yeah.
The displacement of U4 as 0, when I feel like if you moved the location of node 4, it would affect how things are loaded.
This is a wall.
Well, yeah.
The wall cannot move.
I know it can't move, but it's not like its velocity is 0, it's displacement is 0. That's what
Displacement. Displacement.
Okay.
We're not talking about velocity here, it's about displacement.
Okay. I figured that was like relative to a point. Like,
yeah, displacement. It's not, if displacement is 0, there's no velocity, of course. But in all our, let's say, FEA is still a structure analysis. It's a continuation of mechanics materials. Our structure does not have velocity. Yeah, everything is in equilibrium.
Like choose element 5 be the top left range. Like what if you didn't go in the same order you did, but mess up the math? Or would it all work out?
If element 5, sorry.
If you chose element 5 top left range and element 1 is the bottom right, would it mess anything up? Then
You mean move 5 here and 1 here? So good question. Let's I can show you. What if we have this is 5, right? And this is 1. Doesn't make it anything different. So let me calculate for you. So now our element 1 is here, and K is still equal to 1. The thing change is that I need to change this one and this one and this one, this one. Now our element 1 extended to node 3 and node 4, right? So U3, U4, U3, U4. And let's delete this component, because now our element 1 is at, and also delete this one. Our element 1 is +1, -1, -1, +1. Make sense? Now our element 5 becomes connected to node 1 and node 2. So let's change this one to and we need to add. So now this becomes 5, -5, -5, +5. And everything else is same. You still delete boundary condition and everything, right? Does this make sense? Yeah, okay, great. It's the so I just want to make consistent with our FEA textbook. In the FEA textbook, they say it's the element force, but element force in our FEA textbook is actually the same thing as what you learn in the mechanical material. Is the internal force. Yeah, so internal force has its own sign convention. Whenever it's tension, the internal force is always positive. Whenever it's compression, internal force is always negative. That is our definition, sign convention of the internal force. Or if you remember some like more advanced content in mechanical materials, internal force is integration of stress on the cross section of the cross section, right? So let's say if I apply a tensile force, generate tension in this spring element over this bar element, I cut from here, and the internal force on this cross section is whatever normal stress on this cross section, I integrate this normal stress over the cross section. So we know that whenever I have tension, the normal stress should be positive. Integration of the normal stress over the cross section should be positive. When I apply compression, the normal stress should always be negative, and the integration of normal stress over the cross section is always negative. So that is what the element force P here means, and also the same idea of the internal force in mechanical materials. Same thing. Sorry, what? Yes, yes.
Doesn't know the distance, so like how come we're multiplying that thickness by the sum of the forces?
You're talking about bar element or spring element? Spring element. K is stiffness. Yes. So what you learned before you come to FEA class is K times the elongation equal to force. And now our elongation becomes Uj minus Ui. That next to here. This is what you learned. Yeah. We are not doing anything like different than what you learned before. It's the same thing. So element force, internal force, is always equal to K times delta, elongation. Delta is elongation here. Elongation is always Uj minus Ui. This is what you learned before you come to FEA class. And now what I'm doing here is just, let's say, to generate this tension, we need to have same magnitude, but have nodal force. This is a new idea here. Nodal force at J is positive, at I is negative X direction. That's why I said the Fj is always same sign as the internal force, internal sign, and the internal magnitude. These all three are the same. That's why I have these two equation for written in terms of nodal force, not element force anymore, not internal force anymore. Fj, Uj minus Ui. Now Fi becomes Ui minus Uj, and then put into a matrix, becomes our FEA element matrix equation. So this not contradict with what you learned before.
Last thing,
the unit doesn't change. You can see from here, our example, I intentionally mentioned the unit here. So force, Newton per millimeter. This is the same as what you learned before, right? So same thing here, even though we are a matrix, this is, so Newton per millimeter times millimeter equal to Newton, right? We just have more components. Yeah.
Explain the equation, like the solve the 1, 4.
Solve the R1, R4? Yeah. So R1 is for the reaction force. Reaction force is the external pi force. So basically we are summing F1 and F4, right? And in this 4x4 matrix equation, U1, U4, 0. U2, U3, where to solve it. So to calculate this one, again, back to matrix vector operation, you have this one times this one equal to F1. This one times this one equal to F4. Make sense or not? That's why we have R1, R4. Is this clear? Okay. Yeah. Any other question? We have 4 minutes left. Let's continue next class. Thank you for coming and have a great day. Thank you. I think I got it all. The one thing that I feel like we a little bit more clear is how we decided that these were zero. Is it like based on the? Yes. Yeah. So that's for element 1, element 4. How does that correspond to the matrix? Like what? So it's U1, U4, U1, U4. Yeah, U1 and U4. I'm just trying to figure out how it relates. Like I know what we're doing is we are gathering the matrices for every element. And I'm putting that to 4x4 and using that for what's left. It's just finding out what to eliminate is yeah. The net itself is a boundary condition, which means that it doesn't move. Yeah, you did the corresponding boundary class. So in this example, the grid. Yeah, so the rows and the columns for the and for their gonna be okay, understood. Yeah. Sorry, my elevator got stuck on you. It's fine. But yeah, I think I got it. Thank you so much. Well, you're fine stuck in the elevator. Yeah. That's scary. That's scary. You're welcome.
Yeah, so I'm just still like confused about like where the coefficients are like coming from, like the.
So you have this one times this one equal to F1, right? So it's -1 times U2
Okay,
plus -3 times U3.
okay,
And so this -1, -3. And the same thing here, this one times this one equal to F4. So these two are 0, doesn't matter.
okay,
-2 times U2, -2 times U2, -5 times U3.
okay.
Yeah.
I got you.
Yeah.
All right, thank you.
You're welcome. Did you receive the confirmation that I submitted the letter? You submitted the letter? Yeah. Did you receive the confirmation from? The confirmation?